Hello Matthews, welcome to Fergomatics for question A of extension 1. Now we're going to jump straight into the flashback. Alright, this is a pretty hard question, but I'm sure you guys can get your heads around it. Now we've got 2x equals 10. Both sides, you can see there's a 2 here. We just want to get x, and then we look over at the 10. That's got a factor of 2 in it, which is common on both sides. Common factor, divide both sides by 2, that gives us x equals 5. Now, I know that not everyone's going to get their heads around that concept, but that's okay. Hopefully you can keep along with the lesson. Now, getting into the first question, well, the only question, and it's really easy, trust me, given that 4n cubed plus 18n squared plus 23n plus 9 can be written as, n plus 1, 4n squared plus 14n plus 9, prove by mathematical induction that n is greater than or equal to 1. It's 1 times 3 plus 3 times 5 plus 5 times 7 plus any amount of numbers like 2n of n plus 2n minus 1 2n plus 1 equals 1/3 of times n times 14n squared plus 6n minus 1. Now, looking at this given statement here, that means that later in the question, this should hopefully come up, which we could use to help us out to get to our final result. Now, first things first, we're going to make sure this is true in the first place, where it states true for n is greater than or equal to 1. So we're going to do it for n equals 1, our first value, to prove it's true for our first value, alright? So we've got, everywhere we've got an n, so we've got 2n, we've got 2 times 1, minus 1, right? And then we've got the 2 times 1 for the 2n, plus 1 equals 1/3 times 1, plus 4 times 1 squared, plus 6 times 1, minus 1. Alright, so we've substituted 1 into every term of n, which, simplifying that out, we've got 2 minus 1, which gives us 1, and then 2 plus 1, which gives us 3. And then we got 1/3 times 4 plus 6 minus 1. So we've got 4 times 1 squared, which is 4 times 1, which is 4. And you got 6 times 1, which is 6. And minus 1, which is minus 1. So 1 times 3 gives us 3. And then we've got the 4 plus 6, which is 10. Minus 1 gives us 9. So 9 over 3 total, or 1/3 times 9. Dividing that by 3, we've got 3 equals 3. Pretty simple. It works for n equals 1. This is great. Sorry for the moving sounds. I'm sure it's in there. Okay. So looking in here, we now want to assume true for n equals k. Whether that's 1, 2, 3, 4, any amount of terms. So looking at this, we've got 1 times 3 plus 3 times 5 plus 5 times 7 plus any amount of terms, such as up here. And then we've got 2n minus 1, which is now 2k minus 1. And then we got the 2n plus 1, which is now 2k plus 1. And we got equals 1/3 times n, or 1/3 times k. And in brackets, the 4n squared plus 6n minus 1, or 4k squared plus 6k minus 1. Okay, moving this up to the top because I'm so cool. We want to prove true for n equals k plus 1. Alright. Trust me, that's relevant, and you'll see in just a second. So we've got 1 times 3 plus 3 times 5 plus 5 times 7 plus any amount of terms, and then the term before k plus 1 has to be k. So we've still got that term of k in there. So we've still got the 2k minus 1 and the 2k plus 1 in there. But then now we've got another term added on with k plus 1. It's like if n equals 1, then you just have this term, and then once n equals 2, you've got n equals 1 plus n equals 2. So in here you've got the 2, and then in the bracket k plus 1, well, we've substituted for n minus 1. And we've got 2 times k plus 1, which is substituted again for n plus 1. Same thing here, we've just got k, we've got k plus 1. We've got k, we've got k plus 1, we've got k, we've got k plus 1. Okay, and then using our previous assumption, right, n equals k. We've done this just here, did it just before. We have this. So what we've done is with all of these terms, we have put as this, because up here we have proved, well, we haven't proved, but we have assumed that with all this, it equals this. Right? It's the same exact thing as if we were to use it with n, but with k. Now, simplifying this a little, not much, we've just went with the k plus 1s here, and we've just times them by the 2. So we've got the 2k plus 2 and the 2k plus 2 here as well. Moving over and moving up, because I love transitions. You know me, I'm Mr. McGrath, because totally. And then splitting into the left-hand side and right-hand side, because we don't want to touch them. We don't want to touch the right-hand side, sorry, because we want to prove that one statement equals another statement. So if we touch both statements, it's not the same thing anymore. Well, it is, but you're not proving it. So moving the right-hand side up the top to get it out of the way, and moving our left-hand side into the middle, we can then simplify this. So we've got the plus 2 minus 1, which gives us plus 1, and the plus 2 plus 1, which gives us plus 3. Now what I've done is I've now FOILed this. So we've got 2k times 2k, which gives us 4k squared, and then we've got 2k times 3, which gives us 6k, and then we've got the 1 times 2k, which gives us 2k plus 6k, which gives us 8k, and then we've got 1 times 3, which is 3. Here we're multiplying the k into all of these terms due to the fact that out the front here we don't have the 1 over 3 times k, we've got the 1 over 3, and here we do have the 1 over 3 times k, so we just want it the 1 over 3. So 4k squared becomes 4k cubed, 6k becomes 6k squared, and then minus 1 equals minus 1k. Okay, I don't know why I did that. I don't know why I just transitioned, but it did. Moving back up again, we have a look at this. So what I've done here, we've just put all of these terms over the 3, and then here we've times all these terms by 3 to keep it divisible by 3. So we've got 4k squared becomes 12k squared, because 12 divided by 3 is 4. And we've got 8k becoming 24k, because 8, 16, 24, 24 divided by 3 is 8. And then we've got the 9, because 9 divided by 3 is 3, as seen when proving n equals 1, where we had the 3 equals 9 over 3. Okay, so simplifying this now, because we've got a single term of k cubed, which is 4k cubed, so we keep that there. And then we have 2 terms of k squared, so we have plus 6 and plus 12, which gives us 18. And then we've got, for k, we've got minus 1 and plus 24, which gives us 23. And then we've got the 9, which stays 9, right? And now what we're going to do here, once we move it to the side, we're going to pull back our given statement. Given that 4n cubed plus 18n squared plus 23n plus 9 can be written as this. This is just the exact same statement as before, but we're just bringing it back into relevance. So what I'm going to do here with this equation is I'm just going to bring the 1/3 back out the front, and then have the rest of the equation here. Now you'll notice that this little part here and this part here are identical except the n's and the k's, which means they are the same, right? Because we're just using the n's and we're moving the n's around. It's like if we were to use 3 and we had 3 here, 3 here, 3 here, we could put the 3 here, 3 here, 3 here, but we've just done it with the k's. So now what we're going to do is we're going to substitute this for that, as it says we can do that here. And then what we're going to do is expand it out. So we've got 4k squared now, again. And then we've got 8 plus 6, which is 14, but we prefer it this way. You'll see in a second. We get the plus 9 as well, which can be split into plus 5 plus 4. This also has relevance. Sorry. So now if we go next step forward, we have 4k cubed plus 8k plus 4 in brackets. I've just put it into brackets for simplicity. What we've done here is we've moved the 4 over here and then shifted these 2 across one. So we've got the 4 here, and then we've got the 6k plus 5 over here. Now, next course of action is we're going to simplify this term. So we're going to move it back up the top for more working room. And then we're going to do 4k plus 1 squared. You might ask why. It's because by the perfect square, I believe it is, we've got k times k, which is k squared, times that by 4, 4k squared. And then we've got 2k, which gives us 8k when times by 4. And then we've got 1 squared, which is 1, times it by 4 gives us 4. So it still works. This was a little typo, sorry. This should be 5. Expanding this side out now, so this little side, we got the 6k plus 5, which I've split into plus 6 minus 1, which is still 5. just a little manipulation, which then allows us to factor out a 6 out of these two terms, which is a 6 of k plus 1 minus 1. Now, you may not have realized this, but now these terms are equal. They equal the same thing. I haven't touched this one, but they equal the same. Look at this. 1/3, 1/3, k plus 1, 4k plus 1 squared, 4k plus 1 squared, plus 6k plus 1 minus 1, plus 6k plus 1 minus 1. Which means left-hand side equals right-hand side, and proven for all n is greater than or equal to 1 by Pomey. Hooray! Welcome back again, Mathies, for question B of extension 1 for Mathematics for HSC Induction. Now, like last lesson, we're going to have another flashback. Now, this is going to be a little harder than last lesson's flashback, but I'm sure you'll cope. As you can see, we've got a squared in here this time. So we've got 2x squared equals 50. Now, what we want to look into here for squaring, we want it to have it as a term on its own. And we have a problem here, which is 2. And we have a look at the 50, and we notice this, once again, has a common factor of 2. So we can divide both sides by 2, which gives us x squared equals 25. Now, square rooting both sides, we got x equals plus or minus the root of 25 as which gives us x equals plus or minus 5, because negative 5 squared gives us 25. And 5 squared gives us 25. All right, cool. See, not a bad flashback. Now, next HSC question. So we want to prove by induction that 47n plus 53 times 147n minus 1 is divisible by 100 for all integers n is greater than or equal to 1. A little bit different to the last question because we don't have that equals at the beginning. This isn't all that different though. So if we go for 4n equals 1 again, as followed for induction, we can see 47 to the power of 1 plus 53 times 147, 1 minus 1, like in the power. So that gives us 47, because to the power of 1 just gives you the same number, plus 53, right? So plus 53 times 147 to 0, which is 1, which gives us 47 plus 53, or 100. And now 100, I don't know if I have anything extra for here. I do, apparently. So 100 divided by 100 is divisible. So clearly 100, that gives us 1. So therefore 100 is divisible by 100. Cool. So I don't know why that went bold then, but it did. So now we want to assume true for n equals k. It's pretty simple. Where it has n, it equals k. So 47k plus 53 times 147k plus minus 1. Pretty simple. Now, what we want to do here is, because it is divisible by 100, we want to set in a term of 100 here, because we're assuming it is true. So therefore it does equal this, where m is an integer. So if m was 1, 100 times 1 is 100, still divisible, right? Same with 2. 100 times 2, 200. 200 is divisible by 100. So this is just assuming that it is possible. Now, moving this back up to the top, very top apparently, we're proving true for n equals k plus 1 now. So where there is k, we want k plus 1. So we got 47 to the power of k plus 1 plus 53 times 147 of k plus 1 minus 1, which then gives us 47 to the power of k plus 1 plus 53 times 147 to the k. Now, this question's a weird one, and we have to do a few interesting steps to get where we want. So this is the first interesting step. So with powers, when you times together, you add the powers. So if you have 47 times 47, that's like 47 squared, because you have 47 to the power of 1 times 47 to the power of 1. 1 plus 1 is 2. So we've done this. So we've done 47 times 47k, because plus 1 is k plus 1. Right? So it's the same equation, but we just have these split apart. Now this is where it gets a bit weird, but trust me, it works. So we've got this term out the front as usual, and we've got the 53 out the front as usual. But what we've done is we've split it into 47k. So we have 147 times 147k minus 1, because this term, add it together, that's 147 still, and that's to the power of 1. What's minus 1 plus 1? 0. which gives us k on its own, which is up here. So they equal the same. Now it gets weirder again, but continue. So we've just changed the times sign here into brackets. And what we've done here is for each term, we have times it by them. So we've got 100. So for each term, you can agree that we do 100 times 53 times 147 because they're all times. And then you do the same for 47. So what we've done here is we've done that, but we've just written it out. So for 400, we have 100 times 53 times 147 to the k minus 1 plus the 47 version because it's plus 47 times 53 times 147 k minus 1. So what we've done here, we've just swapped these two terms over, so you can see the 47's now over here and the 100's over here. And then we expand it out a little, which is, it looks a bit weird, but it works out in the end. So we've just sectioned it off, changed the times into a bracket again, as we did up here. So just moving this quickly, you can see I've changed it a little. So we've got a common timesing of 47, which means with the plus, we can leave the 47 out the front and then have it like this, because we'd still have 47 times this, 47 times this, 47 times this. So they act the same. And then we leave this out the front. So doing this, you can see that we can highlight this because we've got 47k plus 53 times 147k minus 1, which is this term here. And that equals 100m, which means we can do 47 in brackets 100m plus 100 times 53 times 147k minus 1. See why we've done it? And now what we're going to do is we're going to swap the 100 and the 47 because we can see this as a 47 times 100 times m, which is still 47 times 100 times m. And what we've also done is we've changed the times for brackets, which can finally give us, because we have both sides being times by 100, to 100 of 47m plus 53 times 147k minus 1, because we've still got 100 times 47m, we've still got 100 times 53, and we still have 100 times 147k plus 1, which means it is divisible by 100 for all n is greater than or equal to 1 by POMI. So it's slightly different because we don't have an equals on the other side for the left-hand side, equals right-hand side, but we've still got it divisible by 100, which is the statement we were looking for at the beginning. All right, thank you for this one. I hope you have a good day. I hope this was somewhat understandable for you, and goodbye.